Another example of something we could in principle learn from large-scale structure is neutrino mass. So even a half an eV neutrino suppresses the power spectrum by some non-trivial amount. You could try to learn about it from galaxy clustering or lensing. The difficult part is that this modification appears at relatively small scales, large wave numbers, and so making a few percent measurement at L of order 1,000 is challenging both as a measurement and to interpret it by convincing yourself that you're immune to gas physics and so on is difficult. Okay, let's talk about dark energy. So the only kind of dark energy model that you can write down is a smooth dark energy model. Later on we consider crazily perturbed dark energy that has pressure and anisotropic stress perturbations on small scales. But any dark energy model that derives from a Lagrangian, like a quintessence-like model, is extremely smooth and can at best have small perturbations on horizon scales. So the energy density and pressure, these equations from a slide of Eric Linde's are helpful to see that it's both easy and one has a lot of freedom in working with dark energy. So the energy density and pressure are straightforwardly obtained by getting the stress tensor from this Lagrangian, and so you have there should be a phi dot here. For the kinetic term, that's the potential term, and that's the term you have if there's some clustering. So the equation of state is given by this relation, and so it's easy to see that if the dark energy is dynamical, has a potential, you require the potential to dominate the kinetic term to get W equals -1. So the story is pretty similar to inflation, except that we're now talking about the logarithmic universe. But by constructing any kind of potential you desire, you can get any desired dynamics and therefore any behavior of W. So that's both the ease of doing dark energy stuff and a little bit the frustration that there's no kind of theoretical bias we have about what dark energy might be doing. So how does lensing play into probing this kind of fundamental physics? So this is a theorist version of a lensing measurement. These are three power spectra, L square CL on the y-axis, L on the x-axis. So we're at arc minute scales here, degree scales here. And you can see that, at least with this theorist version, you can get percent level measurements with a really deep 10th of a sky survey of, so here we've shown just 3 tomographic bins, and there's a lot of information to be had by using a bunch of these power spectra, right? With upcoming surveys, even with the CA-based legacy survey, one can have 10 or more of these auto and cross spectra, and then there's a lot of information you can get. So first thing to note is that the power spectrum is smooth. So a single measurement of the power spectrum is not going to give you exquisite measurements of 5 or 10 parameters like the CMB power spectrum does. On the other hand, you have all this redshift binning that gives you information by comparing the growth of the power spectrum as you look at galaxies at higher source redshift. So that's the primary probe of dark energy. Dark energy slows down the expansion, the growth of structure in the universe, and so it changes the relative spacing of these peaks, of these curves. To pick 2 other things that change the shape, there's the spectral index of the primordial power spectrum, and neutrino mass would change the shape of the power spectrum. And as we'll see, modified gravity changes both the shape and this relative and the relative amplitudes. So, I might mention this again later. When we are talking about measurement, systematic errors, what do we really need to do, it's worth keeping in mind that we don't need to measure everything about the power spectrum. If lensing's primary power isn't constraining some particular kind of physics parameterized by a few numbers, then it's worth noting exactly what effect we are looking for and whether or not a particular systematic we care about can mimic that effect. One does want to control all systematics, but at the end of the day, it's worth keeping the simplification in mind so we don't get too depressed. Also note that we have not just the 2-point function, but cross correlations between the foreground galaxies and the background shear, clusters, as you heard, 3-point functions, and so on. Okay, so for the rest of the talk, I'm mostly going to talk about modified gravity. So this is the idea that we don't need dark energy. We can modify the Friedmann equation if gravity is not described by general relativity on large scales and at late times. So we can weaken it in some sense, and making up a theory that does that is not easy. It's much, much harder than writing down the Lagrangian for quintessence. And moreover, if you do manage to write down the theory, chances are very, very high that it's dead on arrival. Because unlike the dark energy, when you write down a theory of gravity, you inescapably predict phenomena that are related to clustering and expansion at all scales in the universe. And so there are very tight measurements in the solar system that agree with GR. And so it's very non-trivial to get agreement with the data. Nevertheless, this is a major preoccupation of theorists in the last decade and continues to be. So the types of theories that people consider are motivated by higher dimensional scenarios. As you probably know, in string brane world theory, it's extremely contrived for a universe to have 3+1 dimensions. So we must think about the fact that our universe may have 4+1 or 9+1, 10+1 dimensions, and for some reason we don't sense the others. But these high dimensional scenarios can have subtle effects, not so subtle for the expansion of the universe, but subtle for every other purpose, because they modify the Friedmann equation. For example, the DGP scenario has a Friedmann equation that looks like this. And so there's a regime in which the second term dominates, which there's a regime in which it produces an accelerating universe. Let me leave it at that for now. Other more prosaic scenarios involve just changing the gravitational action by adding terms. So lose the simplicity of the Einstein-Hilbert action and just add, say, a polynomial or a rational function of R and see what happens. You quite generally have additional fields that couple to the Ritchie scalar. That's the original Brans-Dicke scenario, and these guys can be rewritten as scalar tensor theories. And then you have Mond and Tevis that I won't talk about. So, since we're among friends, I'll just take a short digression to discuss some personal issues that I have. I noticed this morning that I had written string theorist, but that's not really, it's just string theory. There's issues with. So why is that? I mean, especially for lensing, I mean, we're looking at really, I believe, a situation in which few or even 5% measurements of lensing may well reveal the existence of high dimensions. So I love that. I mean, let's do it. Notice that while I'm talking about string theory, I subconsciously started adding like a lot of exclamations. It's kind of dramatic business. So I do believe this. On the other hand, string theory is like theory we've never seen in modern physics, in the last century or two. You have, this is one of the most influential papers of the year. I have nothing against Mr. Berlinde, but I did look at this paper. It says that gravity doesn't exist. Newton may have had some ideas, and Einstein may have had some ideas, but they're just kind of an illusion. It just kind of arises naturally due to entropy gradients that are motivated by something called the holographic scenario.